Welcome to Hydroplate Science. I'm Kevin Elam. In our debut video, we're going to be producing a series of videos to explain the hydroplate theory by Dr. Walt Brown. In this series, we're going to try to produce videos with a lot of hands-on explanation of phenomena that we can see in our lives with props that we hold in our hands, but the phenomenon applied on a worldwide scale. Now, before we get to the hands-on stuff, we need to look at an overview, and that's what we're going to do today. Were you like me when you were in school and you were taught various things that just did not seem to make sense? Do you remember the pictograms here that we have of an animal laying on the ground, and over time sediments settle on the animal. They continue to settle over years, and after centuries the animal is now encased in sedimentary material. It hardens to rock, and we have a skeleton. I remember being in school and thinking, this does not work this way. This is not how it works. When's the last time you saw an animal lay on the ground, be eaten by scavengers, and not be eaten by worms and microbes, and basically be turned to nothing within weeks or months? This is not how it works. Consider river valleys. I'm acquainted with, in my life, the Mississippi River, the Rock River, Tennessee River. This happens to be the Rhine River. Everyday things that you see. Now, we were taught in school that this river used to be up at the level of the plateau. Notice the bluffs are several hundred feet high, and the river has taken millions of years to erode its way down to its present level. Well, excuse me, if this river were millions of years old, where are all the scar marks coming down the side of these bluffs? These bluffs can run for miles before you have side channels coming into the main river. If this bluff were there for millions of years, you'd have all kinds of erosion scars on the side of that bluff. It seems to me the river was, this valley was carved by a much larger river flowing down the river, eroding down the bluffs sideways. And this river that you see now is much smaller than the river that carved this valley. This would be Farmer Brown's field, and you can see that there's an erosion cut through his field. And you'll notice that this erosion cut is not caused by a little trickle of water flowing down for a very long period of time. Basically, it's carved by a gully washer. Notice how the gully washer fills the valley from bluff to bluff and carves the valley lengthwise down the valley. Now, these are just a few of the everyday observations that you could go through that make you skeptical of what you've been taught in school. If you are nodding your head right now, this video series is for you. What my plans are is to publish a series of videos explaining this book, In the Beginning, Compelling Evidence for Creation and the Flood, written by this man, Dr. Walt Brown, PhD in mechanical engineering from MIT. Walt was a longtime military professor and director of science laboratories, and he retired from the military as a full colonel, and he founded the Center for Scientific Creation. And you can go online and read this book. This book is not a pocket book. It is not a little pamphlet. It is a very hefty book full of all kinds of material with lots of references. And this is the 8th edition. You can get it in hard copy, but this 8th edition is not the latest. There's a 9th edition that is online. You can find it at creationscience.com, online book. Walt retired from the military to write this book. Walt has retired the Center for Scientific Creation, leaving the explanation and the sponsorship of this book to the next generation. And that's what I plan on doing. In the Beginning is divided up into 2 sections. The first part contains over 100 categories of evidences that refute the theory of evolution. The number keeps changing as he updates his online book, but the 131 categories of evidence actually have many subparts. There are many hundreds of evidences that refute the theory of evolution. Part 2 of this book explains his hydroplate theory, hence our name, Hydroplate Science. I plan on producing videos to explain the hydroplate theory. I'm going to go after part 2. I'm going to leave part 1 alone for the moment. Given time, I will circle back and I will cover part 1 as well. But part 1 is not unique to the hydroplate theory. Other creationists can address these particular evidences, and many do. Now, the way Walt lays out the hydroplate theory is he starts with his starting assumptions. Now, everybody that searches to research the origins has starting assumptions. It's just that most people don't tell you what those assumptions are. Now, Walt lays his out. He tells you what they are. Assumption 1. The Earth originally existed with one supercontinent with granite flooring. Assumption 2. 1/2 the water currently on the Earth's surface was originally in one interconnected chamber about 30 to 60 miles below the surface. Assumption 3. A tensile crack initiated in the granite plate. Now, let's talk about that third assumption right now. The whole point of Walt's thinking was to lay out the starting assumptions and then apply the laws of physics from that point and see where it goes. And he found that it explains all the major features of the Earth very well. So let's talk about that third assumption. Is this a third assumption, or is it just a consequence of the first 2 assumptions? If the Earth did contain a layer of granite rock on top of a layer of water that was sealed in under the plate, deep underground, tidal forces caused by the moon and the sun, happening about twice a day, would have stretched and deformed that granite plate twice a day for however long. And that water would have heated up and become very pressurized. It's already under high pressure under the layer of 30 to 60 miles of granite. But the heating up of that water would have increased the pressure more and more and more until something would have happened. Could that pressure of the water underneath cause the tensile crack in the granite layer, and that started everything from then on? So is this assumption, number 3, an assumption, or is it a consequence? If it's a consequence of the first 2 assumptions, Walt starts with 2 assumptions, and everything stems from that. We have the granite layer, 30 to 60 miles thick, on top of a layer of water. Now, granite is not floating on top of the water. It merely seals the water in. The granite is much higher than the stack of granite that it can withstand with its compressive strength. So basically, the granite in the lower part of this layer is constantly flowing like putty, as Walt would say, to seal in the water. The water has no way to escape. Below the water, we have basically basaltic rock. The tension crack develops. That tension crack would keep expanding. It would go in opposite directions at about the speed of sound in rock. It would not stop until the pressure, the tension in the granite has subsided. So it's going to circle the Earth until somewhere on the other side of the Earth it's going to intersect itself. Now, the reason it's not going to be terminated before that point is if the pressure in the water is what is causing the tension in the granite. The crack is propagating at about the speed of sound in granite. The pressure wave of water, the crack would also propagate down through the granite crack, down to the level of water. The pressure in the water under the granite plate is extremely high. However, the pressure now, suddenly, when this crack propagates down to the top of the water, the level of water, you have atmospheric pressure here. There would be a pressure wave that will propagate in the water in all directions at about the speed of sound in water, which is about half the speed of sound in granite. So this crack is going to propagate, and everywhere that crack propagates, the water underneath it is still going to be the high pressure that you have here. That's why the crack propagates until it reaches itself somewhere on the other side of the Earth, where the water pressure beneath the crack now has reached atmospheric pressure, and the crack stops. The other thing to notice is that the water instantaneously after that crack propagates down to the level of the water is under very high pressure, atmospheric pressure just above the water layer. Water will be ejected out hypersonically. Very high rate of flow of water. That water will erode the edges of the granite cliffs on either side of the crack. It will erode it quite rapidly because the water is flowing very fast. Play this again. Granite will be crushed. Not only will it be eroding off the sides of the cliff, a granite cliff about 5 miles high can be supported by the granite on the bottom based on the compressive strength of the granite. Any cliff higher than 5 miles is going to exceed the crush strength of the granite. And so the granite from 5 miles down to the bottom of the base of this cliff is going to be crushing and crumbling away. So that crushed and crumbled granite is going to be carried with the flow of water from beneath. That water will be at a high velocity, as I mentioned. It'll be at such a high velocity that some of that water will pierce, it'll divide the atmosphere like a curtain. It will travel above the atmosphere with such velocity that it would reach escape velocity. It would leave Earth's gravitational field. Now those water and the rock that went with it is in the solar system and becomes satellites of the sun, basically comets and asteroids and meteoroids. Some of the water is not traveling quite as fast, and it will get above the atmosphere up into space where it's going to freeze 150, 200 degrees below zero because it's in the vacuum of space, but it doesn't have enough velocity to reach escape velocity. So it will fall back to the Earth. And that water ice now that's frozen above our atmosphere will fall back to our Earth in a huge hailstorm. And it would bury the plants and animals and so forth that were on the surface of the Earth at this time in the hailstorm, burying them. Some of the water will not have enough velocity to get above the atmosphere, won't freeze, but it nonetheless will fall on the Earth as a torrential rainfall. Once the water level, where the crack was, the widening crack, once it gets deep enough, it shuts off the jet basically. Water will still come out and cover the face of the Earth. So basically there's 4 different things that will happen to that water. Some became comets, some became hail, some became torrential rainstorms, and some just merely flooded the granite plate. Basically the old continents on the Earth flooded them. What would happen when this crack widens to the point that it can no longer constrain the basalt underneath it? The rock below will arch up. This is a well-known fact. This is a well-known phenomenon. It's happened in mines in the past. When you dig a strip mine wide enough, the rock underneath can buckle up. And the reason it does that is because this rock way over here, not by the crack, is in compression. It's being compressed by the granite layer on top. It's under very high compression axially, and it's just like pressure, like being in the bottom of a swimming pool. Pressure acts in all directions. The earth, the mantle, the rock below here is pushing up just as hard as the granite is pushing down. It's being pushed from all sides. It's in equilibrium compression. Once you remove the granite plate on the top to the point that there is no more pressure pushing down on the top of that basalt layer, it will arch upwards. When it arches upwards, it will crack. The top surface of that basalt layer will be in tension because it arches up. It's at the top of the arch, kind of like folding a phone book. The top outside edge of the bend will be in tension. We'll have other videos that hands-on explanation of this. Do this again. When that arches up, it's going to lift the edges of these plates. These granite plates now are going to be lifted up. And they're going to be lubricated by the water layer that still remains underneath the plates. The plates are going to flow to the side. They're going to ride down the hill, lubricated by the water, And basically the force of gravity is going to move these plates. Now these plates are going to continue to move until something happens. We'd already explained that this crack had propagated all the way around the Earth. So on the other side of the Earth, there's the crack. There's the eroded off edge of the granite plate. Well, it arched up first in the Atlantic. So the continents move away from the Atlantic. The Americas move to the west. Asia and Africa move to the east. And they're going to continue to slide downhill until one of two things happen. It's going to reach the mid-oceanic ridges on the other side of the Earth, or it's merely going to grind to a halt on the basalt layer because the water that has been underneath has been depleted. So when it slides to a stop, that's the compression event. This granite layer is going to be compressed because it has now been decelerated quickly. When it decelerates, it's going to thicken up because the forces in this direction, there's going to be a brake applied on the left-hand side. The right-hand side of this plate is going to try to continue to move. It's going to exceed the crushing strength of the granite, and you're going to have crushing of the granite, and it's going to thicken up and get taller. Also, what's going to happen is the bottom of the plate that was sliding, the ground to a halt on the basalt layer, it's sliding. It's going to cause a huge amount of friction, huge amount of weight. Rubbing two rocks together that are this big, tremendous amount of friction, cause a lot of heat. It's going to melt both basalt and granite. You're going to have a layer of magma underneath the granite plate as it grinds to a halt. As I said, the granite plate will be crushed. You will have compressive crushed cracks forming quickly in the granite as it grinds to a halt. The sediments that have eroded, basically all the erosion that's happening by the erosion of these wide channels there of the newfound oceans, the edges of the plates, have been deposited on top of the granite plate. They will be deposited, and we'll explain why they stratify. But you have stratified layers of sediment on the top of the continents. When the granite plate slides to a stop, are going to, with momentum, they're going to buckle and fold. They're going to be just like pushing a rug up against a wall. It's going to buckle and fold. And so the sedimentary layers are buckled. The cracks created in the granite, magma below that is squirted up through the cracks in the cracked granite will be quartz. This quartz is one of the minerals in granite that has the lowest melting point. So it will squirt up through the granite plate, up through the sediments, because it's still under high pressure, causing a lot of lava flows, a lot of flood basalts. And over time, they will cool and solidify into rock. You'll have quartz veins through granite. You'll have flood basalts like the Tibetan Plateau and up in Oregon and Washington, because the granite plates have thickened up. They will be standing above the ocean at very high altitude, and we know that as you go in high altitudes like the top of Mount Everest, it gets cold. The air becomes thin and becomes very cold. The continents at this time would be very high. We'll explain later why the ocean water was quite warm to begin with. It would also have been warmed by the friction of the granite plates sliding over the ocean floor, which was the basalt. So you have warm ocean water, cold continents. The temperature difference is going to drive high winds. The moisture is going to be carried over the continents, and it's going to create a lot of snowfall over the continents. Heavy snowfall because of the extreme, warmth of the ocean waters and the extreme coolness of the top of the continents. Heavy snowfalls that would compress into layers of ice, cause glacial movements on the tops of the continents for many years. The other thing happening, and that would happen for centuries, the ice ages would have happened for centuries. The other thing that would have happened for centuries is that the granite plate now is not in hydrostatic equilibrium with everything around it. Think of a waterbed. You toss a brick onto the waterbed. The brick will sink into the waterbed. The area surrounding the brick, without a brick on it, the waterbed will rise up. So the brick will sink, The other parts of the waterbed will rise up until you reach hydrostatic equilibrium. The granite plate would settle into the mantle. We have confirmed that the mantle barrier is depressed under the continents and not so much under the oceans. So the granite plates would settle over time, taking centuries, to settle into the mantle. Lots of volcanic and earthquake activity at this time. The mantle barrier would be much lower under the continent, and ocean floors would be pushed up just like that waterbed. Now that the continents, after a few centuries, the continents are not standing so high above the oceans, the altitude is not as high, the snow would melt over time until you're basically left with glaciers and other constant snow cover, basically at high altitudes in the mountains, for the high latitudes, North Pole, South Pole. All of the low areas on a continent would have filled with water due to the original flood and the melt off from the glaciers melting. Now, back to the newly uplifted mid-oceanic ridges. You'll notice that we have axial cracks because it arched up. The top layer, top surface of the basalt layer is in tension. It cracked axially. As the granite plates slide to the side, more arching will occur. The mid-oceanic ridge would widen. More axial rifts would open up. But those are not the only cracks that would form in the mid-oceanic ridge. If you look at that mid-oceanic ridge that was lifting up and it's traversing, let's say it's traversing this direction, as it lifts up, you can see that it's arching up as well. So that arching action will cause tensile cracks in the mid-oceanic ridge that will be perpendicular to the alignment of the ridge. So now you have the axial cracks in the mid-oceanic ridges, and you also have transverse or perpendicular cracks in the mid-oceanic ridges. Now sometimes, infrequently, because these cracks, these perpendicular cracks don't have to travel as far, they will cut through that ridge before these axial cracks get there. So there are going to be times where you're going to, if you were to trace down, look at a detailed contour map of the mid-oceanic ridges, you'll see these axial cracks will have propagated up to the transverse crack and stop, and will not be propagated on the other side of that crack. Now, if you look at the entire Earth, as I said, the crack started at one place, traversed the globe, kind of like the seam of a baseball, in a jagged path until it intersected itself somewhere. And you'll see, we'll just explain later that it intersected itself there in the Indian Ocean. You would have, and the edges of the granite cliffs have been eroded away, that this would be the Atlantic, and this would be in the Pacific. Now, when that Atlantic mid-oceanic ridge lifted up, I will play this several times, the continent slid with gravity, because the Earth is a huge mass trying to pull itself into a sphere shape at all times. The granite plates slide with gravity, lubricated by the water in the opposite direction. Playing this again, you'll see that there's a mass shift from the Pacific to the Atlantic. As the Atlantic arches up, Earth cannot stand a void. Their pressures are too great to have a void in this part of the Earth, and so the mass of the Earth will shift towards the Atlantic. It'll shift in the pressure wave that'll pass through the Earth, shape of a cone. This is the Pacific. It will be a shape of a cone, pressure wave passing through here. Mass shifts towards the Atlantic. The plates will have overridden the Pacific Ocean. Because of the mass shift, part of the continent in the Pacific will collapse because there can be no voids here. So there'll be lower pressure here. The plates will crack and subside into the Pacific floor. All of the movement of the mass of the rock will cause lots of friction, lots of heat, will melt the rock, and will create the inner core of the Earth. You have a liquid outer core, and you have a solid core. There are some minerals, nickel and iron, that the melting point is very high. Didn't melt those, but in all of the movements of the rock, they will segregate by density, and you'll have the nickel and iron in the solid inner core, and the liquid parts, the magma that was melted, will settle in the outer core. Little tidbit here is that, did you know the density of the rock just above the mantle outer core interface? The rock is half the density of the magma. The magma is twice as dense as the rock just above. Now in the Pacific, I mentioned the Pacific plate did break off, collapse into the new Pacific floor. There's lots of volcanic seismic activity, a lot of movement of rock, a lot of melting of rock. The granite plates fell and were covered by the magma. Magma on the surface of the Earth does not have the same density as magma at these pressures. We'll cover that more in a later video series. So the Pacific floor is now entirely made of magma, which over time would cool and solidify, basically a flake basalt on the floor of the Pacific. So now what you have here is you have the Atlantic Ocean, this is not to scale, with the mid-oceanic ridge. You have the Pacific that has subsided inwards. It's got a floor of basalt, even though about half the Pacific does, underneath the floor, does have continental crust. You would be left with this, as I said, there was a cone-shaped pressure wave that passed through the Earth. You would have a circular area in the Pacific that would have large cracking, faulting, and is leftover seismic and volcanic activity. It's the ring of fire in the Pacific. Back to a slide that we had way in the beginning. I had mentioned that the water gets ejected at such a high velocity. The water and rock would be, some of it would be ejected above the atmosphere with enough velocity it would have escape velocity. It's now in the solar system, so this is the sun. And now we have a comet that is circling the sun. Everything that orbits in the path of an ellipse. You'll notice that the comet would be at its highest velocity when it's closest to the sun, and it's at its lowest velocity when it's furthest from the sun. This is the way things orbit. We will have other videos we'll explain later about Jupiter being a comet killer. Now, Jupiter is very massive. It's a gas planet. It's the most massive planet in our solar system, and it's the biggest comet killer. It travels the sun in an elliptical path. It's almost circular. Well, it's a comet killer, and I'll play this a couple times here, I'm sure. Comet killer because it's got such a big mass that there will be collisions between comets and Jupiter. There are other comets that will get close enough to Jupiter that Jupiter will tear them apart from tidal forces, and we'll explain that. And then there will be gravitational attraction interactions where Jupiter ejects the comet from the solar system. To show this again, Jupiter is traveling and it's near the circular orbit around the sun. The comet is in its elliptical orbit, and as the comet gets close enough to Jupiter, they have a gravitational attraction. The conservation of momentum and the first law of thermodynamics, conservation of energy, tell us that the momentum and the energy of the system never changes. It may just change from one type to another. So Jupiter has potential energy based on its distance from the sun. It has a kinetic energy based on its speed that it's moving. So does the comet. Well, when they gravitationally interact, some kinetic energy is exchanged between Jupiter and the comet. And in this particular event where the comet was ejected from the solar system. The comet picked up kinetic energy and Jupiter lost some kinetic energy. Jupiter's so massive you really couldn't tell by any change of velocity. It'd be very, very, very small. But the comet's very light. It picks up enough velocity. As I said, there are cases of comets being ejected from the solar system due to gravitational interactions. This is just an overview. We just touched the high points. But there are many, you can see many different features of the Earth that are explained by the hydroplate theory. I will be producing a video for each one of these features. We will explain the characteristics of these features. We'll tell you what they are. What is the mid-oceanic ridge? We'll explain it to you, how it's physically made up, what it looks like. And then we will explain why the standard theory of evolution does not explain that feature, doesn't explain any of these features. And then we will explain why the hydroplate theory does explain them. And you will see that the hydroplate theory is the very best, most compelling evidence for the Earth as it had originally existed with those two assumptions that we described, and based on the laws of physics and what would happen if the Earth were created like that, why it has features like this and why it is the way you see it. It'll take some time for me to make all these videos. This is the debut. This is only an introduction. You might want to review the introduction, the big picture, before we talk about those individual features. I hope you've enjoyed this video. I hope you've gotten something out of it. Now it's going to take me a while to get these videos produced because I am a beginner at these videos. But in the meantime, other resources are available to you. You can read Walt's book online at creationscience.com/online book. Online, it's for free. 9th edition is available. Now, Walt endeavored to write this book to be able to be read and understood by high school students. I think he did a good job. Of course, I'm an engineer and I do understand these topics, but I do think that if you're a high school student, if you were taking the advanced physics, advanced chemistry, DiffQ type classes, it would be a lot easier. We're going to try to boil this down with a lot of explanations of phenomenon, with props that you can hold in your hand. We're going to have more props than you can shake a stick at to explain these phenomena. Other resources available to you are realscienceradio.com with Bob Enyart and Jane Albright. And if you like YouTube videos, you can also look at Brian Nichols' videos. He does very good computer graphics. The parting thought I would like to leave you with is you do not have to be bullied into believing the theory of evolution. Thank you. So this book, the 9th edition, is online. You can read it for free at creationscience.com/online book. Other resources are Real Science Radio. Other resources are Real Science Radio. Other resources are Real Science Radio with Bob Enyart and Jane Albright. And if you like YouTube videos, did you have to feed the dogs now? Really?